everyone, and welcome to today's webinar. I'm Deanna McNeil, Assistant Science Editor for The Scientist, and I'll be moderating our discussion. Today, our speakers, Joni Oka and Sandra Soderholm, will discuss how scientists can use electronic pipettes to execute pre-programmed protocols semi-automatically without the need for pipette adjustments, and accelerate research results while decreasing the risk of errors. Before we begin, I'd like to thank Sartorius for sponsoring today's webinar. We like our webinars to be interactive. We encourage you to send us your questions or comments at any point, and our speakers will address these during the Q&A session following the presentations. To ask a question, simply click on the Q&A tab and type your query into the question box located on the right side of your screen. Our sponsor has provided us with some helpful resources related to today's webinar, and we've posted these in our handout section on the right side of your screen. You can access and download these documents at any time during the webinar. If you've minimized the Q&A panel, simply click on the blue chat button in the bottom right corner to bring it back. This webinar will be archived on the Scientist website, and we will send you the link via email within a couple of days. Please note that you will not be able to download the presentation slides. And with that, let me introduce our speakers. Joni Oka is a product manager in the liquid handling division for Sartorius. After completing his degree in automation engineering, Oka joined Sartorius in 2011, developing services and offerings for laboratory devices. In 2014, he switched to product management and has been taking care of Sartorius pipetting and dispensing instruments ever since. Sandra Soderholm is an application development scientist in liquid handling for Sartorius. She earned her PhD in biochemistry from the University of Helsinki in 2016, where she investigated innate immune responses to influenza A virus. After completing her PhD, she worked as a postdoctoral researcher in Dirk Bouwman's lab at Biozentrum, University of Basel, where she studied Pseudomonas aeruginosa and Staphylococcus aureus in clinical samples with mass spectrometry-based proteomics to identify novel strategies to combat infectious disease and antibiotic resistance. Soderholm joined Sartorius as an application development scientist in 2019. Let's make sure that our slides are up and running. Okay, take it away.
Päälle. Voidaan leikata alkukin pois tästä. Hi, my name is Joni Oka from Sartorius.
And hi, my name is Sandra Soderholm. I'm also from Sartorius. And today we're going to talk about connected pipettes and how they can help you in the lab. So please go on, Joni.
Okay, and today we are going to look generally the advantages of electronic pipette and the advantages of connected electronic pipettes. And then we are going to delve into the more application-specific benefits you'll get. Pipetting is one of the most common and important tasks performed in labs. It's very general utilized. They can often make or break your experiments, and pipetting has been around for a while. Around 1950s, we switched from pipetting by mouth to micropipettes after they were invented. We moved towards multi-channel pipettes, especially in the microbubble plates in 1970s. And in the late 80s, Biohead, part of Sartorius today, introduced a electronic pipettes with the DC motor that really helped and sped up the working. So electronic pipettes have been going strong around 30 years already, and they are getting more and more popular all the time. And today, as I said, we're going to look how they will help you and your work. Laboratories face a lot of different challenges. For instance, increase or pressure to increase the efficiency while maintaining reliability and repeatability of results. Pressure to reduce the time to results. And at the same time, we definitely need to uphold the well-being of employees. while considering your laboratory's productivity, consider the tools used. They can make great impact. If you have a lot of sample throughput, if you have a low sample throughput, a good mechanical pipette might be everything you need. An electronic pipette will help increase your throughput while remaining the flexibility of a mechanical pipette. You can semi-automate some protocols, and it's a good in-between step when you can't justify robotic systems. Electronic pipettes definitely give you the same flexibility as with mechanical pipettes, but they increase the throughput and help you to semi-automate some tasks. Even if a lab has most of the liquid handling needs met by a robotic system, there is very commonly still certain things you need to do with the manual pipettes. All the exceptions are typically handled by manual pipettes. Certain sample handling still performed with manual pipettes, cherry picking, etc. So there's a place for various tools within a lab. A lot of laboratories we've seen, they have dozens of pipettes, but typically only a few tend to be electronic ones. There are exceptions, of course. We've seen labs that are fully equipped with electronic pipettes because of the benefits you get, but very typically only a few of them. We've seen, especially when preparing the 96-384 well plates, users tend to move towards electronic pipettes because they reduce the human error and increase the throughput. Another reason you might move towards electronic pipettes if in case the employee has suffered from some sort of injury due to heavy pipetting with mechanical pipettes. But there are some other reasons, well, that you might consider switching to electronic pipettes, and this is what we're going to discuss next. Electronic pipettes, generally, they make lab work more ergonomic. They reduce the user-to-user variance. They create more repeatable and more accurate results. They can be faster and safer. In addition, if you talk about connected electronic pipettes, they enable pre-programmed workflows and user instructions while performing sample preparation or assay preparations. And this is what we're going to discuss next with a few examples. Electronic pipettes, they are very ergonomic to use. And there are a couple of points to consider here when choosing a handheld pipette. First is the weight and height of the instrument. Shorter pipettes, they reduce the need to lift the arm higher, especially if you work in a laminar flow cabinets or safety cabinets. There's a limited amount of space for you to work in. So the shorter the pipette it is, the better in terms of ergonomic it is. Then the weight. Let's take Picus 2 for an example. It's a lightweight electronic pipette. It's as light as a mechanical pipette, so it's easy to lift around and use. Even during long periods of time, it doesn't strain the user. Next is the operating forces. Here in the slide, you see an example of accumulative forces required to operate pipette through the day, per cycle. Because as it's fully electronic, everything from aspiration, dispensing to tip ejection is electronic. So the user only needs to click a button, as compared to mechanical pipette, where the tip ejection is the heaviest part that strains the user. You'll see the huge difference that the user or the force is required to perform a typical cycle. And as you know, typically you don't perform one cycle per day, but you might pipette many hours a day. So the difference in the end of the day is quite significant. Then user-to-user variance. that's one of the big advantages of an electronic pipette. As the piston movement or aspiration and dispensing is done electronically, the user thumb movement doesn't impact the results. So because pipettes, or electronic pipettes, they reduce the assay to assay variance per person, but especially they reduce the operator to operator variance. Here is results from a study performed by Sartorius, where we divided a large group of people into 3 categories. There were unexperienced pipetters, moderately experienced pipetters, and then experts. The data shows the different groups when it comes to mechanical pipettes. It's easy to see the experience level of a person, especially if you adjust the pipette to lower volumes. So, for example, with 1000 microliter pipette, when you're pipetting 500 or close to 100 microliter, the difference become greater. But when the same users did exactly the same experiment with the electronic pipette, then we tend to, or the results show us that the difference between the user groups gets smaller. So this study showed us that the electronic pipettes definitely help to reduce the variance between the users and brings all the users to expert level. Then if you compare mechanical and electronic pipettes, the electronic pipettes do have capabilities in form of different pipetting modes. They definitely can help you to speed up work and reduce the physical stress required to get the work done. For example, multi-dispensing and sequential dispensing modes in electronic pipettes, they significantly speed up the work when you are filling a plate, for example. Here, multi-dispensing is perhaps the most used mode with an electronic pipette, and can be definitely one of the biggest time savers. It can be typically 3 times faster to fill in a microwell plate, or if you compare it to a mechanical pipette. How it works is you aspirate a lot of the liquid into the tips, and then you dispense the smaller aliquots, typically like 8 or 12 times, depending if you have 8 or 12 channel pipette. If you want to fill in a 96 well plate, you might aspirate 800 microliters and then dispense 10 times 100. Saves a lot of time and reduces the need to move back and forth. Especially, it can be very helpful if you combine it with a plate tracking functions. So if you're working with the microwell plates, they are transparent, and typically you handle a small amount of liquids, and they tend to be also transparent or very lightly colored. So it might be a challenge to remember in which well you need to pipette next. Or if you've ever been in a situation where a colleague walks by and asks you something or tells you a funny story, then you totally can get lost where you need to pivot next. But a plate tracking function can help you to remember, okay, I need to be in C8 next, for example. And the electronic pipettes, they do make the lab work safer with these advanced features like calibration reminders, locking functions, and the connected electronic pipettes, they can provide you instructions, pre-programmed protocols. Here on the screen, we have a 96 well plate example where you are working with a single channel pipette, and it tells you where to aspirate, in this instance from a tube, and then you need to dispense to a B1 well. gives you very visual guidance what to do. But even alone, the electronic pipettes with the reminders, you never forget the calibration date, and you can lock the pipettes until they've been calibrated, or you can also use the locking function in case you accidentally contaminate the pipette or it's been dropped. You can lock it and prevent anyone from using it until it's been serviced. Then speed settings. This is again one of the major differentiator between electronic and mechanical pipette. Electronic pipettes, once you set the speed is constant from the morning to afternoon and also to next week and the next week and so on and so on. Especially if you are working with foaming liquids or viscous liquids, circuit media, something like that, it really helps you to control the speed very repeatably. You can completely avoid the foaming by using, for example, multi-dispensing or reverse pipetting and very slow speed. You can avoid foaming completely. And it's from all the pipetting you are going to do with the electronic pipette. So you don't need to be that careful and introduce a lot of stress towards the user to control the manual pipettes and the pistons. But electronic pipettes, you click button and it uses exactly the set speed very constantly and repeatedly. Final slide from me. Updating the pipettes. The connected pipettes, the manufacturer can provide updates and also upgrades. So you can always be sure that your purchase a pipette today and you can enjoy the updated features down the line and maybe new features, even if the manufacturer is bringing something new. So the investment you did once, you don't lose the value, but you get everything, all the new benefits that the manufacturer is bringing out. And next, Sandra will start to talk about the benefits of an electric pipette in the application. She'll also discuss about the new possibilities that these connected pipettes bring to work and the workflows.
Thank you, Joni. So I will start here with talking about the pipetting then in life science applications. So even though pipettes are used every day in labs, pipetting practices is not a topic that laboratory professionals tend to care about. So many, they are self-taught and have never received a formal pipetting training during their career. So as a result, many scientists may not know when to use forward or reverse pipetting, or how the pipetting technique can affect reproducibility of results. So next I'll show some examples and discuss why electronic pipettes are beneficial in life science workflows. So a bit about reverse pipetting, especially for challenging liquids. So please apply reverse pipetting technique when pipetting challenging liquids. For example, foaming, as Joni already mentioned, viscous or volatile liquids, or if you're also struggling to pipette small volumes. So the picture here to the left guides you through the reverse pipetting process with a mechanical pipette. First, you press the piston button all the way down to the second stop, as far as it goes. Then you go to the vessel with liquid, aspirate it by releasing the button completely. When you then you go to your target vessel, dispense by pressing to the first stop, so not all the way down. After this, there is some liquid left in the tip, which you can discard by pressing all the way down to the second stop. So reverse pipetting, it's also possible with electronic pipette. The steps that I just explained, they're just automatically done for you. So in reverse pipetting, an excess liquid is aspirated into the pipette tip, as I mentioned, but only the volume that you set on the pipette is dispensed. So liquid is then lost due to adhesion to the plastic tip. It's compensated from this excess liquid amount. Reverse pipetting also prevents aerosols and bubbles to form, which is important in case you work with cell cultures. One important thing to notice when using reverse pipetting is that your pipette tip have to fit the total volume plus this excess volume. This is extremely important to keep in mind when you are using filter tips, because you do not want the liquid to touch the filter inside the tip, as this leads to reduced accuracy, loss of sample, and also possible contamination. So here you see a graph of an experiment where HeLa cells were pipetted with an electronic pipette to 96 well plates using either forward pipetting mode with blowout, which generates a bit of bubbles. It's seen here as a blue line. Or then using reverse pipetting, which creates no bubbles here in magenta. So the results, they propose that bubbles, they interfere with even distribution of cells and absorbance-based measurement and generate larger deviation between replicates. Bubbles tend to also have a negative impact on cell health and can interfere with microscope-based measurements, for instance, live cell imaging. So keep in mind that multi-dispensing mode on an electronic pipette, it works similarly to reverse pipetting. And it's also recommended for cell seeding. So you can combine pipetting steps into a complete protocol or workflow on most electronic pipettes. Here's an example of a protocol where mixing steps were combined with pipetting the target volume when seeding cells, here in graph, the first graph, plate 1. Or then no mixing steps were applied before seeding cells, so in graph B, plate 2. Each dotted line is cell confluency in one well over time. So for plate 2, where no mixing was performed or programmed between the seeding, the variation in cell confluency between wells was higher than for plate 1, where you had a mixing programmed in the workflow. qPCR, it was a topic on everyone's lips during the COVID-19 pandemic. Electronic pipettes can save more than 50% of time it takes you to pipette the qPCR assay on 384 well plates compared to mechanical pipettes. The time saved is mainly thanks to the multi-dispensing mode, for example, when pipetting master mix to the plate. The plate tracker mentioned earlier by Joni guides you so you won't pipette into the wrong well. In case of sample replicates, you save also time by multi-dispensing the RNA or DNA samples. So pipetting practices, they can greatly affect the reproducibility of sample preparation and ultimately the outcome of, for instance, cell-based assays. So in cell-based assays, as an example here, removing the cell culture media from microvell plates with too high speed can cause cells to detach, for instance. Adding details regarding how pipetting steps should be performed, they are often omitted from published protocols, even though these can be very crucial for how reproducible the assays are in the end. So in this example, the modes, the speeds, and the advanced functions on electronic pipettes were added to a lentivirus titer assay protocol to ensure high reproducibility of the assay. The readout of the assay was performed with the live cell analysis system. So connected electronic pipettes, they open up a whole new dimension of traceability and user guidance for sample prep workflows and pipetting protocols. With the newest electronic pipettes on the market, you're able to make workflows, for instance, in a mobile application, which then automatically selects the most optimal pipettes for the workflow that you have available, sends the pipetting settings, the volume, speed, and mode to the connected pipette via Bluetooth. It also automatically does the switch between the different pipettes depending on the step in the workflow. Additionally, gives the graphical overview of each step in the workflow. So all these features are particularly helpful when working with long and very tedious workflows. On the slide, there's an example of a serial dilution workflow. It is currently instructing the user to dispense 200 microliter to well C1 on a 96-volt plate. Once the user presses the operating button on the connected electronic pipette, the task will happen, so the liquid will be dispensed, and then the pipette will automatically set to the volume, speed, mode required for the next step, or the app will just automatically connect to another pipette if this is required. Yeah, so yeah, thank you for your attention.
Yeah, please ask any questions. We'll do our best to answer them.
Thanks so much for that presentation, Joni and Sandra. As a reminder to the audience, you can submit your questions at any point during the webinar using the Q&A tab up in the top right corner. So we can get started with some questions. Joni, what else besides choosing an electronic pipette can researchers do to address user-to-user variability that you mentioned?
Oh, that's a good one. First thing is the training. So if all the lab personnel have been trained for pipetting and they've been training together for, especially for the liquids that they're using. So as explained during the presentation, different liquids require quite a bit of different pipetting. So I would say that's the number one. And electronic pipettes is a very good supportive action to that.
Thank you. Another question for you, Joni. Is it possible to use one speed on an electronic pipette for every workflow?
Yeah, again, I'm going back to the difference of the viscosity of liquids and different properties of liquids. I think Sandra had a very nice example of a foamy liquids. I would definitely use a much slower speed for foamy liquids or viscous liquids than for aqueous liquids or water-like liquids. So definitely highly recommend to vary the speed based on the liquid that you're pipetting.
I see. Sandra, did you want to add to that at all?
No, that's correct. Yeah, Joni covered it.
Perfect. Sandra, you mentioned filter tips in your part of the presentation. What else can researchers do to prevent contamination?
Yeah, so filter tips is definitely one important part. Then also to use reverse pipetting technique that I mentioned, because that forms usually less aerosols and so on. Then also it's important, of course, to change tips after each pipetting step, or every time you by mistake, for instance, touch something else than the liquid or the vessel that you're supposed to touch. Those are important parts. Then you can also prevent contamination by really keeping your pipettes clean. So clean them routinely before and after you are done with your work. Use autoclavable pipettes, or at least pipettes that can, which lower parts can be autoclaved. And then also the storage of pipettes is important. So store the pipettes in a pipette stand away from dust and dirt. That's very important.
Perfect. Thank you. And Sandra, you talked quite a bit about the reverse pipetting, like you mentioned. Is reverse pipetting suitable for kind of all applications? I know you talked about specific types of liquids, but could you talk a little bit about, when researchers can use reverse pipetting?
Oh, yeah. So reverse pivoting you can in principle always use whenever you want. But it's really a bit, choosing the most suitable technique is, well, it's a bit application dependent. But I would say that reverse pivoting might be a little bit slower to execute, and it might then also increase the need of reagents and samples, like the consumption will be increased a bit when you use all the time reverse pivoting. So in cases where valuable reagents or samples are used, and they don't really have any proper liquid properties that increase the difficulty of liquid handling, like for instance they're not very high viscous or so on, then you might just want to use forward pipetting, for instance. But in principle you can always use reverse pipetting.
I see. Okay, perfect. I think that might be all we have time for questions. So thank you again. Thank you to both of you for that discussion. We appreciate your presence here today very much.
Thank you.
All right, thank you very much.
If anyone in the audience has further questions, please consider reaching out to the speakers directly. Their contact information is shown on the screen. As a reminder, the webinar will be archived on the scientist's website, and you'll receive an email notifying you when the on-demand webinar is available. Please make sure to follow the scientist on social media for further updates on future webinars. I'd like to thank everyone who took the time to join us today, and particularly those of you who shared questions and comments. On behalf of the scientists, I'd also like to thank our speakers once more, Joni Oka and Sandra Soderholm, as well as our sponsor, Sartorius. Thanks so much, everyone, and goodbye.